Section 4.5 are graphs of sine and cosine functions. So in order to work with various graphs of sine and cosine functions, we need to know what the graphs of sine and cosine look like. So one way that you can generate the graph if you don't have it committed to memory is you can actually use the unit circle to graph it very quickly. So in the same way that the easiest points on the unit circle for us to label were the 90 degrees, right? There's 0, 1, 1, 0. We can see just from the unit circle itself that cosine, which are our x values here, will never go beyond 1 and never go in this direction beyond -1, right? Everything has to live on the circle. Similarly, sine will never go above 1 or below -1, and that's the range of each of those functions. So we know those 90-degree marks correspond, if we start at the x-axis, right, we're at 0, pi over 2, pi, 3 pi over 2, 2 pi. So I'm going to do the same thing on the cosine graph. We've got 0, pi over 2, pi, 3 pi over 2, and 2 pi. So if I want to graph the graph of sine, all I have to do is plot the values at each of these angle measures straight off the unit circle. So for sine, I'm going to read the y-coordinates as you go around the circle. So at 0, sine is 0, right? Sorry, let's label these 1 and -1. At pi over 2, we're up at 1. At pi, we're back down to 0. At 3 pi over 2, we're down at -1. And at 2 pi, we're back to 0. So remember, you don't just connect these dots in a straight, jagged pattern. It's a wave. It curves. So it curves around, curves back down, and it continues, right, forever in both directions. So every rotation, one revolution around the unit circle gives you one wavelength of the wave, and then it would just repeat and repeat. For sine, we do the exact same thing, except now I read the x-coordinates as I go around. So at 0, cosine is 1. At pi over 2, it's 0. At pi, it's -1. Then we're back to 0. And then we go back to 1. So once again, when I connect these, they're nice, smooth curves. And we can see we get the same wave-like motion for cosine. These are actually the same wave. We can just see that if I take this wave and shift it over pi over 2, it would line up perfectly with the sine wave. So cosine and sine are the same wave shifted by 90 degrees or pi over 2. And a little bit later when we get into our identities, we'll see that one of the identities is the following. Sine of 90 degrees minus theta is cosine theta. And similarly, cosine of 90 minus theta is sine theta. Obviously, I could replace 90 degrees with pi over 2 and the same identity would hold. And so this, you can visually see why this identity holds because of the graph. If we shift sine back pi over 2, it lines up with cosine. And so these waves are just offset by pi over 2. To look at a general sine or cosine wave, so we learned back in exam 1 that we could shift, translate, right, flip things, move them around. We have a general wave equation that we can use for sine and cosine. So notice here there's a slight variation on this general wave function than the textbook gives. And the reason I personally prefer this one a little bit better is because this correlates directly to what we learned in exam 1 about shifts and translations and reflections of graphs. So one thing I want you to keep in mind, the capital A, B, C, and D that I'm using in these equations, the symbols are irrelevant, okay? We can replace these with any letters that we want. We can use Greek letters, we can use upper and lower case letters. People might mix the order of these up. So what you need to make sure you understand, it is the position in the equation that matters, not the letter being used. So it's where the value falls in the equation. So if we multiply a number or a function out front by a constant, it stretches the function vertically by that constant. So if we put a 2 in front of a function, it doubles all the y values, and so it stretches it vertically by 2. And that's what the a in this function does. A normal sine and cosine wave has an amplitude of 1, right? So if we change that value in the front, we're stretching the peaks and valleys or the crests and troughs of the wave up, or we could shrink it down if we used a number like 1/2. So that's what changes what we call the amplitude of the wave. You can calculate the amplitude directly by looking at the maximum value of the wave, subtracting its minimum value. If we look at the graph, max minus min, right, gives you the total vertical distance from the top to the bottom of the wave. When we cut that in half, it now gives you just the distance from the midpoint up. So on the wave that I've drawn, this represents the amplitude, and this is also an amplitude. So amplitude is a positive quantity. However, it is possible I could throw a -2 in front of sine. And so the way you would read -2 is -2 would really be read as -1 times an amplitude of 2. And those two numbers are doing different things. The 2 is stretching the amplitude, so it goes up to 2 and down to -2. The -1, when you multiply a function by -1, it reverses the signs, right, or reflects the graph over the x-axis. So if you see a negative value in front of a sine or cosine wave, it's reflecting it over x, and then it's stretching it or compressing it by the appropriate value. B in this equation, right, notice here that the B is times x minus c. You've got parentheses here. B is known as the frequency of the wave. So how often is the wave coming by? On a sine or cosine wave, the frequency is 1. That's why when you just look at sine of x, there's just a 1 in front of the x. And what we mean by that is a sine wave comes by once every 2 pi. But if I multiply that value by a constant on the inside, so we learned back in Unit 1 that if we do f of c times x and c's on the inside, we're stretching or compressing the graph horizontally. But remember, it has the opposite effect. So if I put a 2 here, I'm actually compressing the graph by a factor of 2. If I put a 1/2 here, I'm stretching the graph by a factor of 2. So things we do to inside of functions have the opposite effect as what the numbers kind of tend to tell us. So for a wave, if we want to measure how quickly or slowly the wave's passing, because the normal wavelength is 2 pi, we use 2 pi over the time period. And so what it's now telling you is, as compared to a normal sine wave, how frequent or infrequent is this wave? C is the phase shift. So the phase shift allows us to slide the wave left or right from its original position. So this is why I prefer this version of this equation. And I am gonna make sure to tie in all the examples to the way the book is explaining it. But the phase shift, right, we said, well, if we have a minus c inside the function, we're shifting it right. If we have a plus c inside the function, we're shifting it left, right? Because we said anything you do inside the function, it actually has the opposite effect of what the numbers look like they're telling us. So if I look at this, this is shifting the wave c units to the right. So if you're visually looking at the graph of a wave, you can see if it's shifted right or left, and then adjust the number when we're plugging it into the function. D, when you add a number to the outside of a function, right, you're adding that value to any of the y values you would have originally gotten. So we're shifting the graph up or down. So a positive D is shifting the wave up, a negative D is shifting the wave down. We can also calculate that directly. So if we go back to sine and cosine, well, if I add the max and the min and divide by 2, what D really represents on this graph is the midline of the wave. So for our function up here, if y is just sine of x, then if I write it in terms of a, b, c, and d, right, The wave has an amplitude of 1. It comes by once every 2 pi. There is no phase shift because it's in its standard position, and there's no vertical shift because it's in standard position. But also, look at the value of d. It's 0. Y equals 0 is the middle of the wave. So mathematically what you're doing and why this works, this formula works, is what it happens when you add two things and divide by how many you have, right? So if you add two things and divide by 2, you're averaging them. So by looking at the max and the min and dividing by 2, right, we're finding the middle or the midpoint of the wave. Now, it's very cumbersome to write a wave out in this notation. So frequently what we do is we calculate the A, B, C, and D, and we might do something like this. So I could have a wave with an amplitude of 2. Let's call it a sine wave. I could say its frequency is 4, and I'm shifting it pi over 2 to the left, and then I want to shift it down 5 units. So we usually don't express the wave like this because this gets a little cumbersome to write all these brackets and parentheses. So what we do for simplicity is we distribute the 4 across. And when you multiply 4 times pi over 2, you get 2 pi. So if I graph these two waves in a graphing utility, they're identical, they're the same. But in this wave, I can actually see the graph move pi over 2 to the left. Down here, a really common mistake students make is they would say, oh, the phase shift is 2 pi to the left. And that's not what actually happened. So this number, when it's written in this form, is really the frequency times the phase shift. And you would need to divide by your b value to actually see the phase shift. So if I take 2 pi and divide by 4, it factors it out, and I can see the phase shift was actually pi over 2. So that's kind of where the formula in the book is, where they tell you that phase shift, and I think they use little c over little b, and what that's actually doing is just taking this number, dividing out or factoring out the b to give you back the phase shift. So we're going to look at this. We're going to do several problems, and I'm going to show you how to graph a wave when you've been given the equation and how to read a graph and generate the equation for the wave.